So today we're going to be looking at alcohols. And one of the things that we want to start thinking about is we're going to group reactivity into functional groups. And we're going to start to think about broadly how certain classes of functional groups have certain patterns of reactivity. So the functional group of an alcohol is an OH, and it's bonded to any type of sp3 hybridized carbon. That oxygen is also going to be sp3 hybridized. So we have two sp3 hybrid orbitals that form a sigma bond to the carbon and the oxygen. The remaining two sp3 hybrid orbitals each contain an unshared pair of electrons. When we think about naming alcohols, we're going to use the same IUPAC structure that we have used for alkanes, alkenes, and alkynes, which is to say that the parent chain is the longest chain that contains the OH group. We're going to number the parent chain in the direction that gives the OH group the lowest possible number. And then we're going to change the suffix from E to OL. So common names of some alcohols are typically followed by the name alcohol. So while we'll use the IUPAC name, we'll also use alcohol upon occasion. So take a moment, practice naming these structures. You need to press pause so you have as much time as you need. And again, remember, you're using the same conventions for naming that we've been practicing all along. Take a moment and evaluate the way that you name these compounds. If you need to, go back and refresh yourself on the rules for naming alcohols. Now, alcohols that have more than one hydroxyl group, so two OH groups are named diols, three OH groups are named as triols, and then any OH groups on adjacent carbons are called glycols. When we think about unsaturated alcohols, then we want to make sure that we also include the naming for the double bond. So remember, instead of AN for single bonds, we're going to use EN for double bonds. A hydroxyl group is shown by the suffix OL, and then we're going to number the chain to give the OH the lower numbers. Go ahead and take a moment, name this compound. Did you remember to include trans, or E, which stands for entgegen, regarding the double bond? Please make sure that you're thinking about its orientation in space as well as the numbering and naming. So when we're thinking about alcohols, one of the primary roles that we see alcohols take in living organisms is hydrogen bonding. So this is the attractive force between a partial positive charge on a hydrogen and a partial negative charge on a nearby oxygen, nitrogen, or fluorine atom. So the strength of hydrogen bonding in alcohols is approximately 2 to 5 kcals per mole. These hydrogen bonds then are considerably weaker than covalent bonds. For example, a covalent bond for an OH bond is 110 kcals per mole. We see here several different representations of hydrogen bonding. Notice, right, one of these shows the partial charges. Another actually shows the hydrogen bonds in space. And we can actually see the way that hydrogen bonds start to affect the actual physical state of a compound like water. It's important that we make the observation that you can have hydrogen bonds both intramolecular, so between molecules, as well as intramolecular, within a molecule. So inter is between, intra is within. So for the antibiotic erythromycin, I want you to take a moment and see if you can spot where the hydrogen bonds within the molecule are. Were you correct? Did you guess correctly? Take a look at the partial negative and partial positive charges. That's always going to give you an indication of where you can draw your intramolecular hydrogen bonds. One of the things you'll notice for alcohols is their boiling point. Because of this hydrogen bonding, we're going to see significant changes in their boiling point. For example, if I compare something like ethane with ethanol, notice the difference in boiling point. We also see significant differences in solubility, and this is all due to hydrogen bonding. We've also talked about how most alcohols are about the same or slightly weaker acids than water. So when we think about an aqueous solution of alcohol, that's typically going to have a pH that's close to that of pure water. If we think about properties of alcohols in the context of other compounds, right, we have some examples of very strong acids, weak acid, alcohols, and then water. That reference point is something you're always going to want to keep in mind. In the presence of strong acids, the oxygen atom of an alcohol is going to behave as a weak base. We're going to observe proton transfer from the strong acid as it forms an oxonium ion. Thus, alcohols can function as both weak acids and weak bases. Alcohols also react with metals such as lithium, sodium, potassium to liberate hydrogen gas and to form metal alkoxides. So sodium is oxidized to Na+, and H is reduced to H2. Alkoxides are somewhat stronger bases than OH-. They can be used as nucleophiles in nucleophilic substitution reactions. They can also serve as bases in beta elimination reactions. Water-soluble tertiary alcohols react very rapidly with HCl, HBr, and HI. They are low molecular weight, and so if we think about primary and secondary alcohols, they're going to be relatively unreactive under these conditions. Water-insoluble tertiary alcohols tend to react by bubbling gaseous HCl through a solution of the alcohol, dissolved in diethyl ether or THF. Primary and secondary alcohols require concentrated HBr or HI to form alkyl bromides and alkyl iodides. Now, if we think about drawing the mechanism for the reaction of 2-methyl, 2-propanol with HCl in the presence of water, think about the hint that's below. We'll review these mechanisms shortly. Remember, there are several other types, though, of reactivity that alcohols can undergo. So, for example, thionyl chloride, SOCl2, is the most widely used reagent for the conversion of primary and secondary alcohols to alkyl chlorides. I want you to think about the mechanism for this reaction. Can you propose a reasonable mechanism? So the actual mechanism is quite interesting. The hydroxyl oxygen is going to attack the electrophilic sulfur, and then from the tetrahedral intermediate, we're going to eject a chloride. This new chlorosulfite ester rearranges by breaking the carbon-oxygen and sulfur chloride bonds, and then forms the RCl bond and a new sulfur-oxygen bond. Now, it's interesting to think about the stereochemistry of these reactions. Why does SOCl2 give retention? So because the alcohol attacks SOCl2, and after expulsion of the chloride and deprotonation of the oxygen, a chlorosulfite is formed. It's the carbon-oxygen bond breaking with the expulsion of Cl- that forms CO2 and an intimate ion pair. The chloride then attacks the carbocation from the same face, which results in the retention of stereochemistry. This is called an SNI mechanism, or a nucleophilic substitution with internal return. If we compare that with inversion in the presence of pyridine, this is because we actually have an SN2 reaction. So in this case, we have our chlorosulfite, and then pyridine is what attacks the sulfur. We displace the chlorine, and then we have backside attack of a chloride ion, and the result of that is inversion. You're going to need to be familiar with both of these mechanisms and be able to compare and contrast them. So, as a quick recap, thionyl chloride plus an alcohol gives retention of configuration. Thionyl chloride plus an alcohol plus pyridine gives inversion of configuration. We can also see elimination of an alcohol to form an alkene, and that is going to occur, right, under certain types of conditions. So if we have a primary alcohol, it has to be heated at high temperature in the presence of an acid catalyst, such as H2SO4 or H3PO4. If we have a secondary alcohol, it undergoes dehydration at somewhat lower temperatures. If it's a tertiary alcohol, it often requires temperature at or only slightly above room temperature. So I want you to take a moment and try practicing drawing mechanisms for the following reactions. Note, these are all elimination reactions. So take a moment, think about what you know, think about what evidence you could use to propose a reasonable reaction mechanism. And again, press pause if you need a little bit more time. Let's check our work. Did you draw the correct products? Were there any products that you drew that perhaps were the minor products, products that were less favorable? If so, why? Well, let's go back to Zaitsev's rule. So when isomeric alkenes are created, the more stable the alkene, that is the one with a greater number of substituents on the double bond, is generally going to be the molecule that predominates. That's Zaitsev's rule. So let's draw the two possible products and ascertain which one is going to be the major product. Did you draw 2-butene as the major product? If so, then you have a solid understanding of Zaitsev's rule. If you're not sure, then it's a great opportunity to go back and revisit several of the examples that we've talked about previously. So take a moment, draw the mechanism for the dehydration of 2-butanol with HCl in the presence of water. Remember, the acid-catalyzed hydration, of an alkene and dehydration of an alcohol are competing processes. So if I have large amounts of water, then I'm going to favor the formation of an alcohol. If I have scarcity of water, or if I have experimental conditions where I remove my water, then that's going to favor the formation of an alkene. Now, one of the other ways that we see alcohols reacting is in oxidations. The oxidation of a primary alcohol gives an aldehyde or a carboxylic acid, depending upon the identity of the oxidizing agent and experimental conditions. Oxidation of a secondary alcohol is going to give a ketone. One of the most common oxidizing agents in chemistry is chromic acid. Chromic acid, oxidation of one octanol, is going to give octanoic acid. Note, octanol, the aldehyde, is not isolated. That's because it's so reactive that it goes quickly to the octanoic acid. Now, if I wanted to oxidize a primary alcohol to an aldehyde, I would have to use pyridinium chlorochromate, or PCC. This is a particular reagent that's specialized to mildly or gently oxidize a primary alcohol to an aldehyde. So, for example, the PCC oxidation of geraniol gives geranial, the aldehyde. Remember, tertiary alcohols are not oxidized by either of these reagents. They are resistant to oxidation. As a recap, let's consider the following problem. Ethanol can be oxidized to an aldehyde and to a carboxylic acid. Draw the structure of the aldehyde and the structure of the carboxylic acid. Then, think about a suitable reagent and reaction conditions for the oxidation of ethanol to form the carboxylic acid. Finally, draw the structure of the alcohol containing 4 carbon atoms, which would be resistant to oxidation. And last but not least, draw the structure of an alcohol containing 4 carbon atoms, which can be oxidized to a ketone. Next time, we're going to take a look at thiols, ethers, and arenes. Thanks again for your attention. Have a great day.